Okay, we are talking about a new unit, starting Unit 8, which is all about inference for categorical data, chi-square. So back in Unit 6, we talked about inference for proportions, which came from categorical data as well. And then in in Unit 7, we talked about inference for means, which is obviously quantitative data. But in Unit 6, we just compared one proportion to a hypothesized proportion, or we compared two proportions. But in this chi-square unit, we'll be able to compare lots more proportions like we did with the M&Ms. So seeing whether our bag of M&Ms match the proportions that the M&M company put out for each color. So it's like carrying out multiple Z-tests at one time. So comparing, red with orange and red with yellow and red with green and red with blue and then orange with yellow, orange with green, and so on. So it would run all of those tests at the same time feasibly for one of these chi-square tests. So we're starting out with the test for goodness of fit, which in your book is section 14.1. I didn't realize that I'd left that on the slide. This is actually in our new units, topics 8.2 and 8.3, which are called setting up a chi-square test for goodness of fit and carrying out a chi-square test for goodness of fit. So topics 8.2 and 8.3 are all about this chi-square test for goodness of fit. And there are two other chi-square tests that we're going to learn about: the chi-square test for independence or association and the chi-square test for homogeneity. All right, so when we are talking about these new chi-square tests, in the last units, we talked about inference procedures for comparing proportions of successes for two populations or treatments, but sometimes we want to examine the distribution of a single categorical variable across a whole population. So the chi-square test for goodness of fit allows us to determine whether a hypothesized distribution seems valid. This method is useful in fields like genetics, where the laws of probability give the expected proportion of outcomes for each category. You really don't need to write down this whole slide, but you will want to write down a couple things coming up. The idea of the chi-square test for goodness of fit, and we abbreviate that chi-square GOF, G-O-F, and chi-square, actually, you can abbreviate as well. Let me see if I can turn my pen on here. As Greek letter chi, square. So you can say chi-square GOF test on the AP exam, and that's acceptable. So it's comparing the observed counts in our sample with the counts that would be expected if the null is true. And the more the observed counts differ from those expected counts, the more evidence we will have to reject the null. So in general, the expected counts can be obtained by multiplying our sample size by the proportion or the probability in each category according to the null. So the proportion of M&Ms that we had for each color put out by the M&M company, I forget what they were, but 20% is red and 15% orange or whatever, we would take those proportions and multiply by our sample size, because each of us had a different number of M&Ms in our bag, right? So if I had 52 M&Ms in my bag, then I would multiply that by each of the proportions. But if you only had 39 M&Ms in your bag, then you would multiply 39 times each of those proportions from the M&M company. And obviously those proportions are the same as the probability. If you selected an M&M at random, you would get that color. So you could also say those are probabilities. So the chi-square test statistic measures the distance between the observed and expected counts relative to the expected counts. And you'll see how we calculate that statistic here in a little bit. The chi-square distributions are always made up of positive values because we square, obviously, when we're working with these values, so they're always going to come out positive. And the distribution will always be skewed right because they're always positive values. The skew becomes less pronounced, so I guess you could say more normal, but the chi-square distribution will never become exactly normal. But it definitely will be less pronounced as the degrees of freedom increase. So in a chi-square Goff test specifically, the degrees of freedom is the number of categories you have minus 1. So for our M&Ms, I think we had 6 categories, right? Red, orange, yellow, green, blue, and brown. So minus 1 would be 5 degrees of freedom. And the chi-square Goff test should be used when you're looking at the distribution of proportions for one categorical variable, not for 2. That's a different test. So if we're looking at the distribution of proportions for just one single variable, this would be a chi-square Goff test. All right. So then, just as a reference, so you can see what those would look like, with 1 degree of freedom, the chi-square distribution is drastically skewed right. With 4 degrees of freedom, it's still definitely skewed right, but it's not so drastic. With 8 degrees of freedom, you can see it's becoming more normal looking. I don't really want to say that. Maybe I should just say more symmetric, not as drastically skewed to the right. And you don't need to know this for the test, but for those of you guys who really, really, really like the math involved, the mean of a chi-square distribution is always equal to its degrees of freedom. And as long as the degrees of freedom is greater than 2, then the mode of the chi-square distribution, that chi-square density curve, is the degrees of freedom minus 2. So those are just interesting things to note if you're super into the math. But you don't need to know those for the AP test. All right, so let's go through the steps in a chi-square Goff test. First step, obviously, to state our hypotheses. So our null hypothesis would be just use the context of the question. That's going to be way shorter. The other option is to list P1 equals, whatever. So say it was P1 is the red percentage, so P1 equals 0.25. P2 for orange would be 0.15 or whatever. I forgot what the percentages were. But then you'd also have to define P1 as the proportion of all M&Ms that are red, and P2 is the proportion of all M&Ms that are orange, and so on. So that takes a while. I would highly recommend you just use the context in the problem. And so for the alternative, you're going to use the context too, or you could say at least one of these proportions is incorrect. Depending on the context, that might be shorter. I don't know. Kind of up to you. And so then step 2, right, for any test is name the procedure. So this would be a chi-square Goff goodness of fit test. And I don't have to put this in context because I used the context in step 1. So that's really nice. And we are not, by the way, going to do confidence intervals for chi-square. We're just going to do our hypothesis test. So you don't have to worry about the steps in the confidence intervals. We're going to be using that 5-step process for tests instead. Step 3 is our state and check the condition step. We still need to state and check our conditions, but I am not going to sin anymore because the end doesn't apply. Chi-square distributions are never going to be normal or even approximately normal. So we're going to see if the conditions check, but I'm going to spell C funny. I'm going to spell it S-I-E. So our S condition is still the same. The data need to be from an SRS from the population of interest or from a randomized experiment. And obviously that's going to have to be stated in the question. The I is still exactly the same. When you sample without replacement, you have to check that N is less than or equal to 10% of capital N, the population size. And you obviously have to show that check. I'm going to simplify this from in the past. We said when sampling without replacement, the observations need to be considered independent. I really don't think after reading more this year in the grading that we have to say that anymore. I think we can just say when sampling without replacement, N has to be, lowercase n has to be less than or equal to 10% of capital N, and then we have to show that's true. And for this, I don't think we have to say anything about independence. I might still talk about independence when we're dealing with proportions or means, but for chi-square, I don't. And then our last one is now going to be E instead of N. E is that all expected counts have to be greater than or equal to 5. And for a Goff test, we will be the ones calculating those expected counts. So we will have to show that those are all greater than or equal to 5. And I'll show you how to do that again in a sec. All right, and so then our step 4, my favorite, right, is do the math. So for the chi-square, you looked at this with the M&Ms the other day, but we calculate chi-square by finding the sum of all of our observed minus expected values squared, and then dividing that by our expected values. So our chi-square statistic is our observed minus our expected for each of our different categories. In the M&M's situation, it would be the observed number of reds that you got minus the expected number. Square that value, add those all together for each of the different colors, and then divide each of those by their expected count. You know what? I just realized I wrote this wrong. Okay, forget that. I should have written okay, that's bad. The sum of the observed minus expected squared over the expected, all added together. Sorry, I just wasn't thinking there for a sec. So you subtract the observed number of red minus the expected number of red, you square that, then you divide by the expected number of red, and then you add all of those together. So you'd add that value for red, for orange, for yellow, and so on. Sorry, I was just not looking at that carefully. Okay, and then for our degrees of freedom, right, I already told you how to get degrees of freedom. It's the number of categories minus 1. Number of categories minus 1. Oops. And then we also need to write down our p-value, right? And we can get our p-value from the chi-square table or from our calculator. I usually just get it off my calculator, but we can also get it from the chi-square table. And then step 5 is our conclusion and context. So same as it ever was, because the p-value, I was writing p-value with a lowercase p, I think, but no biggie, either way. Because the p-value, which is whatever, is greater than or less than alpha equals whatever, I reject or fail to reject the null, there is or is not evidence that blah, blah, blah. Same as it's always been, okay? So let's try one. Let's start with a pretty easy one, and then I'll do a little bit tougher one. Let's start with an example of a die. So suppose you roll a die 60 times and you get 12 ones, 9 twos, 10 threes, 6 fours, 11 fives, and 12 sixes. Do you have evidence that the die is unfair? What does that mean, unfair? Or what does it mean if a die is fair? It's weighted so that each side has a probability of occurring 1/6 of the time, right? 1/6 of the time I should roll a 1, 1/6 of the time a 2, and so on. But I know when I roll a die, I don't exactly expect a 1, a 2, a 3, a 4, a 5, and a 6 one time in 6 rolls, you know? I would expect I roll it and I get a 2, I roll it and I get a 3, I roll it again and I get a 2, I roll it again and I get a 5, you know, so in 6 rolls I wouldn't expect exactly one of each number. Same thing if I rolled it 60 times, I shouldn't expect to get exactly 10 of each number. So are these values off enough that we could consider the die unfair? So again, my null hypothesis, I could list out P1 should equal, P2 should equal, and then say P1 is the proportion of all rolls that would come up with a 1, and P2 is the proportion of all rolls of a die that would come up as a 2, and so on. But that takes a long time. So let's just go with our context. We're looking for evidence that the die is unfair, and we always look for evidence for the alternative, right? So what would our null be? Our null then should be the die is fair. And so then the alternative would be the die is unfair. That makes sense? Okay, so then step 2, right? We name our procedure and we don't need context this time. Yay, because we put the context in step 1. So step 2 is super short. We just write chi-square Goff test. That's it. That is naming the procedure. Okay, then we go on to step 3, which is state and check our conditions, right? So for our S statement, remember we're going to see, spelled funny, SIE, if the conditions check. So for our S statement, we need to say that this is an SRS from the population of interest or from a randomized experiment. This is rolling a die 60 times. So I guess you could technically consider it an experiment. I just said it's a sample. And then we have to check that. So because rolling a die in it of itself is a random event, then I can consider those 60 rolls a random sample of all die rolls. So I said for the S, the data need to be from an SRS from the population of interest. And since rolling a die is a random event, I can consider these 60 rolls a random sample of all die rolls. And so then for our I, remember, we don't have to say anything about independence this time. We can just say that when we are sampling without replacement, which this would be, the more I think about that, I think we could say this is with replacement, because I roll a die and I get a 2, I could roll a die and get a 2 again. So I think I'm going to skip that step in this one. I think we're okay without that one. And then our E, remember, is all expected counts must be greater than or equal to 5. No 10s anymore like we had with our proportions and our means. We have to have 5. I guess it would just be for proportions. Means we had to have 30. So all expected counts must be greater than or equal to 5. So to calculate the expected counts again, remember you take your sample size and you multiply it times the proportion for each category. Our categories are rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, and rolling a 6, right? So our expected count for rolling a 1 would be our sample size, which was 60, times the proportion, or the probability, remember, was another way to say that, of rolling a 1. What is the probability when I roll a die that I get a 1? It's 1 out of 6, right? Which is obviously 10. Shouldn't I, if I roll a die 60 times, expect 10 of those rolls would come out to be a 1, and 10 would be a 2, and 10 would be a 3, and so on? So can I just do quotes the rest of the way down? I think I missed one somewhere. Oh no, I'm good. Okay. So then I would say all expected counts are greater than or equal to 5, because they all came out to be 10, which obviously is greater than 5. Okay. And so then step 4, my favorite step, we get to do our math. So for our math, we need to calculate our chi-square. Remember again, I'm going to write it correctly this time. It's the sum of our observed minus expected quantity squared over expected. And we have to show our work. So because this is going to be 6 separate little values, they call them contributions to our chi-square, because I'm going to do it for rolling a 1, for a 2, for a 3, for a 4, and so on. Remember, I can use an ellipsis, a dot, dot, dot in the middle, And so I can show my first two values. So I could say it would be equal to, for rolling a 1, I don't remember what they said. We got 12 ones, we got 9 twos, and we got 12 sixes. I'm going to show the first one, the second one, an ellipsis, and then the last one. So I just have to remember 12, 9, 12. Okay. So going back to my math, I am going to do the observed, which was 12 ones, minus the expected, which was 10, squared over my expected, which was 10, plus, because I'm finding the sum, 9 twos minus 10, quantity squared, over 10, the expected, plus ellipsis, plus, and then go to my last one for sixes, there were 12, minus I expect 10, quantity squared, over 10, and then I can go to my calculator. So everybody's got this in their calculator. If you have a TI-84 or newer, if you have an old school TI-83, then I can give you this program that I adapted. So for your TI-84, you can just go into your lists. So go into Stat, Edit, and then clear out if you have anything in List 1 and List 2. And in List 1, we're going to put our observed. So let me go back to, the directions that they gave us. They had 12 ones, 9 twos, 10 threes, 6 fours, 11 fives, and 12 sixes. So let me show you my calculator here. Where is my camera? There we go. That's what I put into List 1, okay? And then I'm going to go into List 2 and put in the expected values, which were all 10, right? Because I would expect 1/6 on each of those times my 60 rolls is 10. So I put all of those into my calculator like that, okay? Then we're going to go into our stat and over to our tests, and then scrolling up is going to be shorter than scrolling down because our chi-square test, our chi-square Goff test is going to be pretty close to the bottom. You do not want C, the chi-square test. That's for independence association or for homogeneity. We don't want that one. We're doing the chi-square Goff test, which in my calculator is letter D. Okay, so I select that one, and it says, where are your observed values? We put our observed values in List 1. Now this is super cool. It's not saying, or no, sorry, that's for the next chi-square test. This, we had to put in the expected ourselves. So we did put the expected in List 2, and our degrees of freedom, let's see, we had categories 1, 2, 3, 4, 5, and a 6. Those were the different things you could roll on a die. So degrees of freedom would be 6 minus 1, or 5 degrees of freedom. And so we can calculate this. You can draw it if you want to see what the graph looks like. But right there, I got a chi-square value of 2.6 and a p-value of 0.761 about, okay? So let me go back. Oops, I didn't mean to take a picture, but that's okay. Let me go back here to our math, and we can say this is equal to, right, this is our chi-square, is equal to 2.6. Our degrees of freedom was 6 minus 1, 5, and our p-value was approximately, what was it, 0.761. Okay. And so I could put all of these into my calculator by hand, just in case you wanted to check it. I could do the 12 minus 10 quantity squared, squared divided by 10, and I could do plus the quantity 9 minus 10 squared divided by 10, and I could do plus the quantity let's see, I'd have to go back to whatever my observed was. Quantity 6 minus 10 squared divided by 10 plus the quantity 11 minus 10 squared divided by 10 plus the quantity 12 minus 10 squared divided by 10. And I do indeed get, where'd my calculator go? 2.6. So calculator obviously much faster if you just put your data in your list, but you can do this by hand to get the chi-square value as well. And then let me show you how to use the table in case you need to use your table on the AP test, in case your calculator horribly would die on you or something. Okay, so if I go to my chi-square table here, we had 5 degrees of freedom, right? And so we would look for our chi-square value as close as we could get to it on here. Ooh, my chi-square value is not on here because it was really small, right? It was 2.6. So I could just assume that if I read up here that my p-value is going to be greater than 0.25. Obviously, these are going down. So if my chi-square value is smaller than 6.63, which it is, 2.6, then my p-value is going to be greater than 0.25, which it is. It was 0.761. So with the table, it gives you a rough estimate, but not a very precise one. We can do much better with our calculator, okay? But if on the AP exam they were to tell you the probability, and you needed to, or they tell you maybe it's statistically significant at the 5% level, and they ask what is the test statistic, then you could say, here's my 0.05, you could look up however many degrees of freedom, say you had 9 degrees of freedom, and you could say then your statistic is greater than that 16.92, because anything greater than that would give you a value farther out in the tail, so your p-value would be less than 0.05, so you'd reject. Okay, so that's just how you could read the chi-square table. All right, so let me go back to our notes again. And so what does that mean as our conclusion then, if our p-value is 0.761? So just the same as we always do, because the p-value 0.761 is greater than alpha, I don't think they gave us one, so assumed to be 0.05, I fail to reject H naught. There is not evidence, and I go back to the context of the question, to conclude that the die is unfair. Okay? So that's it for a chi-square Goff test. Let's try one more really quick though, because sometimes we will actually need to calculate those proportions ourselves, like they do in biology class. So scientists want to investigate the genetic characteristics of offspring that result from mating parents with known genetic makeups. They use the rules about dominant and recessive genes to predict the ratio of offspring that will fall into each possible genetic category, and then they mate the parents and classify the resulting offspring, and then use that chi-square Goff test to assess the validity of their hypothesized ratios. Okay? So, back to that good old Punnett square. If the biologists are going to mate two fruit flies that have genetic makeup capital R, lowercase r, capital S, lowercase s, where a capital R equals red-eyed, a lowercase r equals white-eyed, a capital S equals straight-winged, and a lowercase s equals curly wings. So if we have the mom, we'll say, on this side, and the dad on this side, and they each had that makeup of capital R, lowercase r, capital S, lowercase s, then here's what would happen, right? They'd get one of the R's from their mom, and they'd get one R from their dad. They'd get one S from the mom and one S from the dad. So they could get both capital letters from mom, and they could, maybe I should have written this one in a red color, get the two capital R's from capital letters from dad as well, which would give them genetic makeup capital R, capital R, capital S, right? And so going across the row, if they get a capital R lowercase s from mom and a capital R lowercase s, or sorry, I said I was going to go across the row and I forgot what I was doing, and still that capital R, capital S from dad, then it would look like this: capital R, capital R, capital S, lowercase s, and so on. So we'd have a capital R, lowercase r, capital S. We'd have a capital R, lowercase r, capital S, lower s, and so on and so forth, okay? I will let you guys, well, I have to fill this in really quick, but you guys can fill this in too. So capitals, lowercase, capital, lowercase, capital, lowercase, capital, lowercase, and then we'd have capital, lowercase, capital, lowercase, lowercase, capital, lowercase, capital, capital, lowercase, capital, lowercase, lowercase, capital, lowercase, and then finally all lowercase. Okay, and so would they end up with red eyes, white eyes, straight wings, curly wings, right? So we're looking at the ratios. So for our, I don't think I made a chart on the next one. No. For our red eyes, oops, that's not red. Red eyes and straight wings, that would be our two dominant traits, right? Oops, straight wings. That would happen whenever we have both the capital letters R and capital S. So let's see how often that happened. And I'll make this purple, let's say. So for red eyes and straight wings, here we've got a capital R and a capital S. Here we have a capital R and a capital S. Here we do, here we do, here we do, here we do, here, 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 and that's it, I think. Yep. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Happened 9 times out of how many squares total? 16, right? So we could leave it as a fraction, or we could say 9 out of 16 is 0.5625. It doesn't matter which way you write it. Then let's go with red eyes, but curly wings. I don't know how they fly if their wings are curly, but maybe that means something I don't understand in biology. Okay, and let's make these, how about green? So red eyes and curly wings. Let's see, so we would have to have a capital R, but then both lowercase s's. That would happen here, here, here. Yep, that's it. So that would be 3 out of 16, or whatever 3 out of 16 is as a decimal, is 0.1875. And then we could have white eyes and straight wings, which would be, let's make this about orange. White eyes and straight wings would happen if I had both lowercase r's and a capital S, which is here, here, and here. That S is supposed to be capital. So we'd have 3 out of 16 again, or 0.1875 again. And final category would be our white eyes and curly wings, which would again only happen if they get both recessive traits from their parents. And I know this is an oversimplification. You guys that are in AP biology know there's probably more to it than this, but for statistics, this is all we need. And so obviously for that white eyes and curly wings, let's make that blue. that only happened once. So our proportion or our probability is 1 out of 16, or what is 1 out of 16? 0.0625. And obviously, if you added up all those probabilities, you'd get 16 out of 16, because that's all the different things that could happen, right? So these are all the different categories, and we're looking at the proportion for each of those categories, and does the sample match this, which is the biologist predicted ratios. This is what we predict would happen in an ideal world, okay? All right, so let me respond to my text message real quick. Sorry, guys. Okay, so now that we know the predicted ratios, then here is what our question talks about. Yes, I picked that picture purposefully. You guys are high school kids. You can handle it. So to test their hypothesis about the distribution of the offspring, the biologists mate a random sample of pairs of fruit flies, and of the 200 offspring, it turns out that 99 had red eyes and straight wings. So what color did I make that? Purple. Red eyes and straight wings was 99. And then I went with green was red eyes and curly wings. And then I went with orange was white eyes and straight wings. Whoops. 49 of those. And then I went with blue for the last one. 10 had white eyes and curly wings. So do these data differ significantly from what the biologists have predicted? Carry out a test at the alpha equals 0.01 significance level. Okay, so walking through our 5 steps. Step 1 would be to state our hypotheses, right? So our null hypothesis is the biologist's predicted ratios of fruit fly characteristics are correct, or the data do not differ significantly from what the biologist predicted, or something along those lines. And the alternative would be the biologist's predicted ratios are not correct, or at least one of these proportions is incorrect, or the data differ from what the biologist predicted, or something along those lines. Okay. And so then our step 2 is super short because we put our context in step 1. Step 2 is name the procedure. It's just a chi-square Goff test, period. Okay. So then our step 3, state and check our hypothesis, or state and check our conditions. Sorry, the whole test is checking our hypotheses. So we're going to see if the conditions check, spelled funny, SIE. So our S, remember, is still our data have to come from an SRS from the population of interest or collected from a randomized experiment. So they mated random samples of pairs of fruit flies. So since these were random pairs that they created, I can say that the offspring can be considered a random sample of the different categories. And so then for our I, for independence, we would have to say that there would be more than, or the lowercase n has to be less than or equal to 10% of capital N. And so there were 200 offspring. So we would have to say that 200 is less than or equal to 10% of capital N, our population size. So in other words, the population of all fruit flies would have to be larger than or equal to 2,000. I guess I should say the population of fruit fly pairs. So there would have to be technically more than 4,000 fruit flies, of which 2,000 are male and 2,000 are female. But either way, I think we're fine. So I do have to say on this one, because there are more than or equal to 2,000 pairs of fruit flies in the world, this condition checks, this condition is satisfied. Something along those lines. Satisfied. Oops. Okay. You cannot just show that why is that not moving? That lowercase n has to be greater than or equal to 10% of little n. You can't just show this math, I don't think. I think you have to show a sentence explaining why. Okay, my program crashed on me. Hang on. Let me see if I swipe it off and open it again, if it'll work. Hopefully it saved my handwriting. Yeah. Okay, cool. Okay, so then all the expected counts need to be greater than or equal to 5. So we have to take our sample size, which was 200, and multiply times each of the proportions or the probabilities. That was what we got from the Punnett square, right? So times each of these. Okay, so we need to write down our expected counts for red eyes and straight wings. 200 times, didn't we have 9 out of 16? And then for red eyes and curly wings, it would be 200 times 3 out of 16. And then for white eyes and straight wings, it was, 200 times 3 out of 16 again. And then white eyes and curly wings is our 200 times 1 over 16. And let's see what all those are. So 200 times 9 over 16 is 112.5. And then 200 times 3 over 16 is 37.5. So the next one's 37.5. And then 200 times 1 over 16 is 12.5. So then I can say all expected counts are greater than or equal to 5, because I can see right there they all are. The smallest is 12.5. Okay. Then on to my math, my favorite step. Do the math. Okay, so remember, we can use that ellipsis as a shortcut. So we can say our chi-square is equal to our first observed value was 99, and then our second is 42 and 10. 99, 42, and 10. 99, 42, and 10. Okay, just wanted to write those down before I forgot. Plus, and then this would be an ellipsis, and plus this last one. Okay, and then I need our expected. Our first expected count was 112.5. Our second was 37.5, and our last was 12.5. Oops. So those again are over the expected. Sorry, I wrote this very weirdly, didn't I? Hopefully you're still following along with my math there now that I have it all written out. And then I can pop these all into my calculator. So I go into my stat edit. You can clear out what we had in there from our die rolls. And we can put in, for list 1, the observed was 99, 42. I don't know the third one. I think it was 49. Yeah, 49 and then 10. And then in my expected, right, we had 112.5, 37.5, 37.5 again, and 12.5. And then I can just do my stat over to tests, up to chi-square Goff test. Remember, not just plain chi-square test. It's got to be the chi-square Goff, goodness of fit test. Our degrees of freedom, how many categories did we have? Well, let's see. We had red-eyed with straight, red-eyed with curly, white eye straight, white eye curly. So that's 4 categories. Minus 1 is 3 degrees of freedom. And then we calculate, and I get a chi-square value of 6.187 about. And my degrees of freedom is 3, obviously, and my p-value from my calculator is about 0.103. I get 0.102873336, blah, blah, blah. So about 0.103. Okay, and so our conclusion in context, because the p-value 0.103 is greater than alpha, now this time remember they gave us an alpha. They said at the alpha equals 0.01 significance level. So since it's greater than 0.01, I fail to reject H0. There is not evidence to conclude that these data differ significantly from what the biologists predicted. All right, and so homework tonight is page 846, numbers 1, 3, and 10. Page 846, 1, 3, and 10. All right, guys, have a great night. See you tomorrow.